This is a presentation for IJCNN 2021 entitled H-GAN, the Power of GANs in Your Hands. Advances in the domain adaptation field reduce the domain gap between synthetic and real data. For this purpose, image-to-image translation methods have proven to be successful. Today, we would like to present such a method called HandGAN, in short, H-GAN, designed to translate synthetic images of hands to the real domain. It is well known supervised deep learning models are data hungry. For this reason, synthetic data generation emerged as a quasi-unlimited source of fully annotated data. Now, synthetic data, even if it is photorealistic, is not representative of the real domain. For instance, a hand segmentation model trained exclusively on synthetic images commonly exhibits generalization issues when segmenting real images of hands. Let's take a closer look at the synthetic hands to see why. Synthetic hands still don't look like real hands. However, they provide full ground truth annotations such as normal maps and instance segmentations. Some have unrealistic shapes and low-quality textures. At a distribution level, they clearly do not approximate real images of hands. Others present uncanny artifacts. For instance, looking at the wrist, we notice undesirable shading discontinuities. In short, synthetic hands provide full ground truth annotations, yet their appearance is not at all realistic. So, why not train a model exclusively on synthetic hands? At a distribution level, there is a clear distinction between the synthetic and real domain of hands. This is what we call synthetic to real domain gap. It is the reason that models trained exclusively on synthetic data commonly exhibit generalization issues in the real domain. Our goal is to bridge the two domains. So let's see how. Given a synthetic dataset of hands, such as synth-hands, and the real hands dataset containing real images of hands, we want to translate the synthetic hands to the real domain. This is, we want to change the appearance of synthetic hands so that they look like real hands. In this way, the translated images would approximate the underlying distribution of the real hands. Thus, they could be used together to train deep learning models. We also want to preserve the shape of the hand during the translation process so that it corresponds to the synthetic annotations. We aim to provide the perfect blend of fully annotated synthetic hands with a realistic appearance that closely resembles the target domain of real hands. For the task at hand, no pun intended, we propose H-GAN, a cycle GAN-based approach featuring perceptual discriminators. Let's see its architecture in detail. Represented in green, we have a generator trained to translate synthetic hands to the real domain. We also need to translate real hands to the synthetic domain. This is with the synthetic generator represented in blue. The data flow is as follows. First, we translate a synthetic hand to the real domain. Then, the resulting image is translated back to the synthetic domain. At this point, cycle GANs do their magic with the cycle consistency loss. It ensures that the generated synthetic hand matches the original synthetic hand. This helps to preserve the skin color and shape of the hand during the synthetic to real translation process. Let's replicate the same pipeline, but now we go in the opposite direction, from real to synthetic. So far, the generators perform the interdomain translation, but how do we know the generated images belong to the target domain? It is the discriminators that evaluate how good the generator's outputs are. In other words, they determine whether the outputs approximate the real or synthetic distributions. To make it all work, generators and discriminators are trained together in an adversarial fashion. Different from vanilla cycle GANs, and our competitors will see later, we implemented multi-scale perceptual discriminators. Let's have a look. Perceptual discriminators consist of stacking convolutional blocks on top of feature vectors. In our case, features are extracted from a pre-trained VGG16 network at 4 different scales. This makes the model learn statistics at different levels of abstraction. In other words, we enforce the interdomain mapping of both low-level and high-level features. This is why H-GAN not only performs simple cross-domain tone mapping, but also addresses structural differences. We'll see more about this later. We implemented 4 models with different discriminators and a number of residual blocks in the generators. First, two conventional cycle GANs, denominated PIC-cycle-GAN4 and PIC-cycle-GAN6. Both use pixel discriminators and ResNet generators with 4 and 6 residual blocks, respectively. On the other hand, we implemented MSH-GAN4 and MSH-GAN6 models featuring multi-scale perceptual discriminators and generators with 4 and 6 residual blocks, respectively. For all the implementation details, feel free to check the provided source code and preprint paper at the end of this presentation. Our main competitor is the HGAN model. Different from our architecture, HGAN implements a geometrically consistent loss to preserve the shape of the hand in the translation. This loss uses the UNet network to segment the shape of a hand. This makes HGAN model not end-to-end and leads to additional memory overhead. The usefulness of the geometrical loss is an open question, as cycle GANs inherently preserve structure using their cycle and identity losses. We see this in our results without using extra losses or architectures, and keeping things simple. Now let's have a closer look at some images generated by each of the models. In terms of sharpness, PIC-cycle GANs tend to perform better. This is because the receptive field of the pixel discriminators is a single pixel. The drawback is that they are prone to one-to-one map the skin color and transfer structural artifacts. Now check the small gaps between the fingers. Notice the MSH-GAN6 model fills these gaps. Here, the geometric loss in the HGAN GAN makes a difference. However, the improvement over the MSH-GAN4 model is not clear. Regarding skin color consistency, PIC-cycle GAN outputs share similarities with the synthetic hands. This is reflected in the perceptual metrics we are going to see later. In this regard, HandGAN not only performs a visually more realistic tone mapping, but also treats structural differences in localized areas such as shading discontinuities. Let's dive into the details. Notice how the H-GAN perceptual discriminator makes the generator to hallucinate hair in the synthetic domain. Moreover, the generator also treats shading discontinuities at the wrist. These artifacts are not found in the real data. For the quantitative evaluation, we want to quantify how similar our generated images of hands are to the real domain. To do so, we compared 2,000 generated hands with 2,000 images of real hands in terms of different perceptual metrics. We have used two perceptual metrics, the Fréchet inception distance and the kernel inception distance. They are based on the difference between distributions representing the source and target domains. The closer the distributions are, the lower the metrics. In the bar chart, the better the model, the darker the blue color is. We observe that our MSH GANs outperform all the other models, including our competitor. This points out that our generated hands more closely resemble the real domain of hands. However, these metrics are statistical approximations to the true interdomain difference. Even if they have proven to be useful as an evaluation metric, they do not guarantee any correlation with performance on real-world tasks. That's why we performed additional experiments to ensure the cross-domain similarity. To this end, we trained the Vision Transformer model to classify images of hands under different configurations. Hands, used for training and testing, were placed on random backgrounds to prevent the classifier from focusing only on their shape. In this first experiment, we performed a binary classification of images of hands into the synthetic or real class. In the bar chart, bars represent the composition of the training set. While the synthetic class doesn't change, the real class in the training set can contain real images of hands, generated images of hands, or a mix of real and generated hands. Colors represent the F1 score of the real hands classified as real and the generated hands classified as real. For instance, the leftmost bar represents a classifier trained only on synthetic and real images of hands. At this stage, the classifier doesn't know what the generated hands look like. If most of the generated hands are classified in the real class, we assume they approximate the real domain of hands. This is precisely what happens. Also, when using generated hands in the training set, results are even better. Now we want the classifier to learn the differences between the real and generated hands. To this end, we trained the classifier on 3 classes. We assume that if the generated and real hands share similarities at a distribution level, the classifier might confuse the 2 classes. If we look at the confusion matrix, we see that 18% of the real hands were classified as generated and 13% of the generated hands as real. This further supports that the hands we generate with our H-GAN model are close to the hands in the real domain. To sum up, H-GAN successfully bridges the gap between synthetic and real images of hands, so it can translate any synthetic dataset of hands to the real domain, better than existing methods. Feel free to check out our source code available on GitHub. Thank you, and thanks for listening.